You carry an assumption about the world so quiet that you've probably never noticed it. It is the belief that if something is real, if it is genuinely there, then science already has a name for it. Someone, somewhere, has measured it and filed it away. But here is what that comfortable belief leaves out. Right now, on the surfaces of two frozen worlds, there is a substance doing exactly what substances do, quietly absorbing sunlight at one exact colour, 5.11 micrometers, and it has no name. When astronomers found it on Titan, the largest moon of Saturn, and then found the very same mark on distant Pluto, out past Neptune, they compared it against thousands of known chemicals, every fingerprint in every archive we keep. Not one of them matched. The substance is plainly there, and by every record we have, it should not exist. So make yourself comfortable and settle in. If you are new here, go ahead and subscribe, because by the end of this, you will see that the map of everything we know still has a quiet, open edge, and it sits closer than you think. Now, let us slowly settle into this. Part 1. The fingerprint that belongs to nothing. There is a signal coming from two different worlds, and nobody on Earth can tell you what it is. It is not a radio message. It is not a flash of light or a burst of energy from some violent event. It is something far quieter than that, and in a strange way, something far stranger. It is a small, precise dip in the sunlight reflected from the surfaces of two frozen worlds, a narrow notch cut into the spectrum at one specific colour. And when the people who found it went looking through every catalogue of every substance that humanity has ever measured in a laboratory, they came back with nothing. No match. Not a close one, not a partial one. The signal seems to belong to a substance that, as far as our records are concerned, simply does not exist. Here is the part that turns a small technical measurement into something that can keep you awake at night. This same signal, this same fingerprint that belongs to nothing, appears on two worlds that could hardly be more different from one another. One of them is a giant moon of Saturn. The other is a dwarf planet far out past Neptune, in the cold outer dark of the solar system. They are separated by billions of kilometers. They have different temperatures, different histories, different skies, and yet they are both wearing the very same unknown thing on their surfaces at the very same color, as if the universe had quietly signed the same name in two places and left us standing here, wondering who wrote it. For most of the time we have been looking outward. The solar system has felt like a place we were slowly finishing. We sent our machines to the planets one by one. We mapped the craters of Mercury and the clouds of Venus. We drove rovers across the red dust of Mars. We flew past the great striped storms of Jupiter and the rings of Saturn, and eventually, after a journey of almost a decade, we reached the last of the classical planets and looked at Pluto up close for the first time. It was easy to believe that the age of genuine surprises was ending, that from here on the story would be about filling in the details of a picture we had already sketched. This discovery is a reminder that the picture is not finished at all. It is a reminder that even the worlds we think we know can still hold something in plain sight that we cannot name. The two worlds at the centre of this story are Titan and Pluto. Titan is the largest moon of Saturn, a world so big that it is larger than the planet Mercury, wrapped in a thick orange atmosphere that hides its surface from ordinary view. Pluto is the small, distant world that most of us grew up calling the ninth planet, a body of ice and rock circling the sun at the edge of the known map. If you were asked to pick two places in the solar system with nothing in common, you might well choose these two. One is a moon, the other orbits the sun directly. One is bathed in a heavy hazy sky. The other has an atmosphere so thin it is almost a rumour. One sits about 1.5 billion kilometres from the sun. The other drifts nearly 4 times farther out. They belong to different regions, different families, different chapters of the solar system's story, and that is exactly why the signal is so unsettling. Because when you point the most powerful telescope ever built at each of them and split their reflected light into a spectrum, the same strange notch appears in both. Not a similar notch, the same one at the same place, to a precision that leaves very little room for coincidence. To understand what was found, you have to understand what a spectrum actually is, and we will come back to that in a moment in more detail. For now, hold on to a simple picture. When sunlight falls on the surface of a world and bounces back into space, it does not come back unchanged. The materials on that surface absorb certain colours, certain very specific slices of light, and let the rest reflect away. When we catch that reflected light and spread it out, the way a prism spreads sunlight into a rainbow, we see dark gaps where those colours are missing. Each gap is a fingerprint. Water ice leaves one pattern. Frozen methane leaves another. Carbon dioxide, nitrogen. All the common substances of the outer solar system, each of them writes its own signature into the light, and over many decades we have learned to read those signatures the way you might read handwriting you recognise. The signal that was found on Titan and Pluto sits at a colour our eyes cannot see, in the infrared, at a wavelength of 5.11 micrometers. A micrometer is a tiny unit, 1/1,000,000th of a metre, and the exact position of a fingerprint at that scale matters enormously, because it is set by the physics of the specific molecule doing the absorbing. Shift the position even slightly, and you're talking about a different substance entirely. So when astronomers saw a clear, well-defined dip at 5.11 micrometers on Titan, and then saw a dip centred at essentially the identical position on Pluto, they were not looking at a vague resemblance. They were looking at what appeared to be the same material, announcing itself twice, across the width of the solar system. The team that found it was led by a researcher named Bruno Bizard at the Paris Observatory, working with a group of colleagues that included some of the most experienced scientists in the study of these cold and distant worlds. They were using the James Webb Space Telescope, the enormous gold-mirrored observatory that has been rewriting our view of the universe since it opened its eye, and in particular they were using two of its instruments, one that reads the near-infrared and one that reads the mid-infrared. Having two separate instruments matters, and it matters a great deal, because it is the difference between a possible glitch and a real discovery. If only one detector had seen the dip, you might reasonably worry that the detector itself was to blame, some quirk of the electronics fooling you into seeing a feature that was not there. But when two different instruments, built on different principles, both register the same notch at the same colour on the same world, and then the pattern repeats on a second world, the case that this is real becomes very strong indeed. So the researchers were confident about what they had. A genuine absorption feature, sitting on the surfaces of both Titan and Pluto, at 5.11 micrometers, carving out somewhere between 6 and 7% of the light on Titan and a slightly smaller slice on Pluto. What they were not confident about, what they could not answer at all, was the only question that really matters. What is it? This is where the story becomes something more than a technical footnote, because identifying a substance from its fingerprint is normally a solved problem. We have spent more than a century building libraries of spectra, measuring how thousands upon thousands of chemicals absorb light, cataloguing every fingerprint we can produce in a laboratory, so that when we see one out in the universe, we can look it up. It is a little like a detective with an enormous archive of fingerprints on file. Most of the time, the match is there. You find your suspect. The mystery, if there was one, dissolves into an answer. The researchers ran this fingerprint against the archive. They compared it to the known ices and organic compounds relevant to these worlds. They checked it against the substances we already know are present, the methane, the nitrogen, the carbon monoxide, the whole familiar cast. And the archive came back empty. Whatever is absorbing light at 5.11 micrometers on Titan and Pluto is not in our files. It does not match anything we have ever measured. The fingerprint is real, and it belongs to nothing we can name. There is a phrase that keeps surfacing when people talk about this result, an instinctive, almost involuntary reaction, and it is worth sitting with, because it is exactly the wrong way to say something true. People look at a clean signal that matches no known substance and they say, this shouldn't exist. You can understand the feeling. We're used to the idea that the universe, at least the chemistry of it, is something we have mostly figured out. Two frozen worlds should not be able to show us a material we cannot identify, and yet, there it is, twice over. The feeling that it shouldn't exist is really just the sound of your expectations breaking. The thing plainly does exist. It is sitting on the ground on two worlds right now, absorbing sunlight, as it has been doing for who knows how long. It is not the substance that is impossible. It is our certainty that was too small. It helps to appreciate how genuinely unusual this is, because clean mysteries of this kind are rare. Most of the time, when a telescope turns up something unexpected on a distant world, the surprise is one of degree rather than of kind. We find more of a substance than we predicted, or it sits in a stranger place than we imagined. But the substance itself is one we recognize, To end up instead with a feature that survives every attempt to explain it away is uncommon, and the researchers did try methodically to explain it away, one avenue at a time. They asked first whether the dip might come from the atmosphere rather than the surface, since gases absorb light as readily as solids do. So they built detailed models of each world's air, including every gas and every kind of haze particle known to be present, and asked those models to reproduce the feature. The models could not. Whatever makes this dip is not floating in the sky. It is lying on the ground. They asked next whether the signal might be a quirk of the instrument, some artifact of the detectors rather than a real property of the light, and that is where the two separate instruments become decisive. A single detector can deceive you, but two different ones, built on different principles, agreeing on the same feature at the same colour, cannot easily be deceived in the same way at the same moment. And when the pattern then repeated on an entirely separate world, the possibility of coincidence shrank almost to nothing. Finally, they asked whether it might be one of the substances already known to coat these surfaces, and they checked, and it was not. Each of these questions closed off an easy answer. What remained, once the easy answers were gone, was the hard one, the interesting one, the one we are here to sit with. A real substance on the ground on two worlds that we cannot name. That is the shape of a true discovery, and it is worth recognizing when you meet it. It is not a wild claim or a leap of fancy. It is the careful, stubborn residue that remains after every ordinary explanation has been ruled out, and it points not outward into fantasy but inward at a specific gap in what we know. That is the tone I want to carry through everything that follows tonight. Not fear, and not the breathless language of a mystery that will never be solved. Something calmer than that, and in the end more interesting. The universe has handed us a word in a language we have not finished learning, and instead of panicking, we can do the patient thing. We can learn about the two worlds this word is written on. We can learn how we read such words at all. We can walk through the short list of substances it might turn out to be and understand why none of them quite fits. And we can look ahead to the machine we're already building to go and touch one of these worlds with its own hands, and perhaps, at last, read the word aloud. But everything starts here, with two frozen worlds separated by billions of kilometers, both marked with the same fingerprint that belongs to nothing, and a small, stubborn dip in the light that refuses for now to tell us its name. Part 2. How to read a world you have never touched. Before we can appreciate what is missing, we have to understand how we ever find anything at all on a world we have never set foot on. Think for a moment about how strange it is that we can say anything about the surface of a moon more than 1 billion kilometers away. No human has been there. For Titan, we have landed a single probe once, briefly, more than 20 years ago. For Pluto, we have never landed anything and likely will not for generations. We have never scooped up a handful of either surface, never held a piece of it, never run it through a laboratory. And yet scientists can tell you, with real confidence, that Titan's surface holds water ice buried under organic sediment, or that Pluto is covered in frozen nitrogen and methane and carbon monoxide. How can anyone possibly know that from here? The answer is light, and the patient science of reading it. Every object you have ever seen, you have seen because of light bouncing off it and into your eyes. The colour of that object is your brain's interpretation of which wavelengths of light survived the encounter and came back to you. A red apple looks red because its skin absorbs most of the other colours of sunlight and reflects the red back at you. A blade of grass looks green for the same kind of reason. Colour, at its root, is a story about which parts of the lighter material keeps and which parts it lets go. Your eyes are already doing a crude version of the science we're talking about every waking second without you ever thinking about it. Now imagine doing that far more precisely. Instead of lumping all the light into 3 broad channels the way your eyes do, imagine spreading it out into hundreds or thousands of fine slices, a smooth ribbon running from one wavelength to the next and measuring exactly how much light is present at each one. That ribbon is called a spectrum, and the instrument that makes it is called a spectrometer. When you look at a spectrum, you're not seeing a picture of an object. You're seeing a graph of its light, a terrain of peaks and valleys, and the valleys are where the story lives. Those valleys are called absorption features, and they appear because of something happening at the scale of individual molecules. A molecule is a small arrangement of atoms bound together, and it is not a rigid, frozen thing. It vibrates. Its bonds stretch and bend and twist, like tiny springs, and each kind of molecule has its own set of natural rhythms, its own preferred frequencies at which it likes to move. When light of just the right colour comes along, light whose frequency matches one of those rhythms, the molecule drinks it in. It absorbs that specific slice of light and uses the energy to vibrate a little harder. Light of the wrong colour passes by untouched. So when sunlight falls on a surface full of a particular molecule, that molecule quietly removes its own special colours from the reflected light and leaves a dark valley in the spectrum exactly where its rhythm lies. This is why a spectrum is a fingerprint. The positions of the valleys are set by the physics of the molecules themselves, by their masses and their bonds and the geometry of how their atoms are arranged. Carbon dioxide vibrates at certain frequencies, and nothing else does quite the same way, so carbon dioxide leaves a signature you can recognize anywhere in the universe. Water leaves its own, methane leaves its own, and because those rhythms are fixed by nature and not by us, the same molecule leaves the same fingerprint whether it is in a jar on a laboratory bench or spread across the surface of a moon of Saturn. That is the quiet miracle at the centre of this whole field. The laws of physics are the same out there as they are down here, which means the fingerprint we measure in the lab is the exact fingerprint we should look for in the sky. Consider a concrete example close to home. When we look at Mars and spread out the light coming from it, we see a strong pattern of valleys that matches precisely the fingerprint of carbon dioxide that we can produce in any laboratory on Earth. That is how we know, without ever having bottled the Martian air, that its thin atmosphere is mostly carbon dioxide, with a little water and a trace of carbon monoxide mixed in. The match between the light from Mars and the light from a jar of gas on a bench is what turns a guess into knowledge. And the size of a valley tells you something too. A deeper valley generally means more of the material is present, taking a bigger bite out of the light. A shallow one means only a little, so a spectrum tells you not just what is there, but roughly how much. This whole method has a history, and it is worth knowing, because it turns the reading of starlight from a piece of magic into a hard-won human skill. It began, in a sense, with a prism and a puzzle. When early scientists passed sunlight through a prism and spread it into a band of colour, they eventually noticed that the smooth rainbow was not smooth at all. It was crossed by a series of fine dark lines, narrow gaps where particular colours seemed to be missing, and at first no one knew what they were. In the early 1800s, a German optician named Joseph von Fraunhofer mapped hundreds of these dark lines in the sun's spectrum with great care, charting their positions without yet understanding their cause. They became known as the Fraunhofer lines, and they were the first hint that light carried a hidden kind of writing. The meaning of that writing was worked out around the middle of the 1800s, when two other scientists, Gustav Kirchhoff and Robert Bunsen, made the connection that founded this entire field. They discovered that when you heat a chemical element until it glows and pass its light through a prism, it produces a set of bright lines at very specific colours, and that each element produces its own unique pattern, as distinctive as handwriting. Sodium always makes the same lines, iron always makes its own, and crucially, those same colours appear as dark lines when light passes through the cooler element, absorbed rather than emitted. The dark Fraunhofer lines in the sun's spectrum were suddenly readable. They were the fingerprints of the elements in the sun itself, written into the sunlight, telling us what the sun was made of from 93 million miles away. For the first time, humanity could determine the composition of a body it could never hope to reach. That was a revolution in what seemed knowable. A philosopher had declared, only a few decades earlier, that the chemical makeup of the stars was precisely the kind of thing human beings would never be able to learn. Spectroscopy proved him wrong almost immediately, and then kept proving him wrong, world after world and star after star. Nearly everything we know about what distant objects are made of, we know through this one method, the patient reading of the dark and bright lines written into their light. When the James Webb Telescope split the faint sunlight reflected from Titan and Pluto and searched it for hidden fingerprints, it was doing exactly what Kirchhoff and Bunsen first made possible, only with a sensitivity and a reach they could scarcely have dreamed of. The mystery at 5.11 micrometers sits at the far frontier of a technique more than a century and a half old, and the fact that the technique has finally met a fingerprint it cannot yet name is not a weakness of the method. It is a sign that we have pushed it all the way to the edge of what we have ever measured. Now you can begin to feel why the 5.11 micrometer signal is such a problem. Reading a spectrum is normally a two-step process. First, you find the valleys. Second, You look them up in your library of fingerprints and read off the answer. Almost always, the second step works. The library is enormous, built from more than 100 years of careful measurement, containing the signatures of thousands upon thousands of substances. When we look at Titan and Pluto, most of what we see is comfortably explainable. There is the fingerprint of frozen methane, there is nitrogen, there is carbon monoxide, there are the broad marks of the hazy organic material that coats both worlds. For decades, the spectra of these two bodies have been, if not simple, at least readable. We knew the handwriting. The 5.11 micrometer feature breaks the second step. The valley is right there, clear and well defined, especially on Titan, where its width has been measured very precisely. But when the researchers took that valley to the library had no page for it. They compared it against the known ices. They compared it against the organic compounds we expect on these worlds. They ran it past the great databases of molecular fingerprints that chemists have assembled, and nothing lined up. The position was wrong for every candidate they could pull off the shelf. It is as though the detective ran the fingerprint through the entire archive, the largest collection of prints ever assembled, and the computer returned no matches at all. Not a criminal we had missed. A person whose prints are not on file anywhere, and who nonetheless has quite clearly been here. It is worth being precise about what that does and does not mean, because this is where wonder can curdle into nonsense if you're not careful. It does not mean the laws of chemistry have broken. It does not mean we have found something supernatural, or something that defies physics. Absorption. At 5.11 micrometers is perfectly ordinary physics. Some molecule with the right internal rhythm is doing exactly what molecules do. What it means is narrower and, honestly, more interesting. It means the specific molecule, or more likely the specific mixture of molecules, responsible for this fingerprint is one we have not yet measured in a laboratory. Our library is enormous, but it is not complete. Chemistry is effectively endless in its combinations, and out on these cold worlds, under conditions we cannot easily reproduce, nature has apparently assembled something we simply have not gotten around to making and measuring ourselves. That is a very different feeling from fear. It is the feeling of standing at the edge of the catalogue and realizing the catalogue has an edge, and it reframes the whole discovery. The question is not whether the signal is real. 2 instruments and 2 worlds have settled that. The question is not whether it obeys the laws of physics. Of course it does. The question is simply this. What is the substance that our libraries have never met, and why is it sitting in the same form on 2 worlds that have never touched and never shared a history? To even begin answering that, we have to go and stand on each of those worlds in turn. We have to understand what Titan is, and what Pluto is, and why 2 places so unlike each other might, underneath all their differences, be running the very same quiet chemistry. So let us leave the spectrum behind for a while, and travel out to the first of our 2 worlds, the giant moon wrapped in orange, the one place beyond Earth where you could stand on a shore and watch a sea. Part 3. The Moon with an Ocean of Air. Titan is the strangest familiar place in the solar system, a world that keeps reminding you of home right up until the moment it terrifies you with how alien it is. Start with its size, because size is where Titan first breaks your expectations. We are used to thinking of moons as small, secondary things, grey and cratered and dead, circling the real worlds that matter. Titan is not like that. It is the largest moon of Saturn and the second largest moon in the entire solar system, and it is bigger than the planet Mercury. If Titan orbited the Sun on its own, we would have no hesitation in calling it a planet. It is a genuine world by any fair measure, more than 5,000 kilometres across, with a diameter about half again as large as our own moons. And unlike almost every other moon we know, it is not bare rock and dust. It is wrapped in a thick, substantial atmosphere, the only moon in the solar system that can make that claim. That atmosphere is the second surprise because it is not some wispy trace of gas. It is denser than the air you're breathing right now. If you could stand on Titan's surface, the atmospheric pressure pressing on you would be about 1.5 times the pressure at sea level on Earth. In terms of the sheer weight of air above your head, Titan has more of it than we do, and it is made mostly of the same gas that makes up most of our own air. Titan's atmosphere is roughly 95% nitrogen, just as Earth's is mostly nitrogen. 2 worlds, hundreds of millions of kilometres apart, both cloaked in nitrogen skies. For a moment that can make Titan feel almost like a cousin, a chilly sibling of Earth. Then you notice the other 5%, and the feeling of kinship starts to shift into something more uncanny. Because that remaining sliver of Titan's atmosphere is largely methane, the gas we know on Earth as the main component of natural gas, and on Titan methane does something extraordinary. It plays the role that water plays here. It is cold enough on Titan, catastrophically cold, that methane can exist as a liquid on the surface, and it moves through a full cycle the way water does on Earth. Methane evaporates, rises, gathers into clouds, and falls again as rain. That rain runs across the surface in rivers. It pools into lakes and seas. Titan is the only other place in the solar system where we have found stable liquid on the surface, standing bodies of it that you could sail a boat across, except that the liquid is not water. It is a frigid mix of methane and its cousin ethane, filling basins near the poles that we have given names, the largest of them called Kraken Mare and Ligeia Mare, seas in the truest sense of the word. That methane cycle deserves a closer look, because it is the nearest thing to Earth's water cycle found anywhere else, and it runs on a substance we usually think of as a fuel. On Titan, methane evaporates from the seas, rises into the cold sky, and gathers into clouds. Those clouds drift and thicken, and now and then release rain, fat slow drops of liquid methane falling through the dense air far more gently than raindrops fall on Earth. The rain carves channels into the icy ground, gathers into streams, and flows downhill to pool in the lakes and seas near the poles. Then it evaporates again, and the cycle turns. Titan has weather in the fullest sense, seasons that shift over its long year, wet stretches and dry ones, even the equivalent of droughts and floods, all of it playing out with methane in the role that water plays at home. There are dry riverbeds near Titan's equator that fill only rarely, and broad basins that appear to have shrunk and grown as the seasons turned. Titan's year is long, because Saturn takes about 29 Earth years to circle the Sun, so each of Titan's seasons lasts more than 7 of our years. The weather changes slowly, on a stately schedule, clouds building over one pole through a long summer and then migrating to the other, and beneath all of this surface activity, most scientists are now convinced, lies something even more remarkable, a hidden ocean of liquid water, sealed under many kilometers of ice, kept from freezing by the warmth of Titan's interior, and perhaps by a little natural antifreeze in the form of dissolved ammonia. If that ocean is real, and the evidence for it is strong, then Titan holds liquid water beneath its crust and liquid methane on its surface, 2 entirely different kinds of sea stacked one above the other on the same world. Then there are the dunes, which cover a large share of Titan's equatorial regions in long parallel ridges of dark material, looking from orbit remarkably like the great sand seas of Earth's deserts. But Titan's dunes are not made of sand in our sense. They are built from grains of the same dark organic material that falls from the haze, the solid products of the atmosphere's chemistry, piled and shaped by Titan's winds into ridges that can run for hundreds of kilometers. So even the moon's deserts are made of the organic snow we keep returning to, sculpted into frozen waves of chemistry. Everywhere you look on Titan, the story comes back to that same falling organic material, colouring the sky, dusting the plains, drifting into the seas and heaping into dunes. It is the connective thread of the entire world, and it is the very thing our mystery is hiding inside. Hold the full picture in your mind, because it is genuinely without equal. Titan has rain, rivers, lakes, and seas. It has clouds and weather. It has a thick nitrogen sky. It has dunes of dark sand stretching across its equator, sculpted by winds. It has, almost certainly, a hidden ocean of liquid water buried far beneath its frozen crust, kept from freezing by the warmth of the moon's interior. In its shapes and its patterns, Titan is the most Earth-like surface we have ever found, and yet every familiar feature is built from the wrong materials, run at a temperature that would kill you instantly. The rivers are methane. The bedrock is water ice, so cold it behaves like stone. The temperature at the surface sits around 94 Kelvin, which is about minus 179 degrees Celsius, cold enough that the very idea of standing there without protection is a kind of joke. Titan is Earth's shape drawn in ice and shadow, a familiar melody played in a key that no living thing from our world could survive. And over all of it hangs the haze. This is the feature that hides Titan from us. The reason that for most of the space age Titan was just a smooth orange ball in our images, its surface a total secret. The atmosphere is filled with a thick photochemical smog, a haze of complex organic particles suspended high above the ground, so dense that ordinary cameras cannot see through it. This haze is not incidental. It is central to our whole story tonight, because it is made by the same kind of chemistry that may be responsible for the mystery we are chasing. High in Titan's atmosphere, sunlight and energetic particles strike the nitrogen and the methane and tear their molecules apart, and the fragments recombine into larger and more complicated organic molecules, building upward in complexity until they form the tiny suspended particles that give Titan its permanent orange veil. Those particles have a name. They are called tholins, and we will spend real time with them because they are the closest thing we have to a suspect. For most of human history, we had no idea any of this was there. Titan was discovered more than 3.5 centuries ago, in the middle of the 1600s, as a faint point of light near Saturn, and for almost all of the time since it stayed a point of light, a mystery wrapped in orange. That changed with one of the most ambitious missions ever flown, a spacecraft called Cassini. A joint effort of the American and European space agencies spent 13 years orbiting Saturn, from its arrival in 2004 until its deliberate fiery end in 2017, and it made Titan one of its central obsessions. Cassini carried radar that could pierce the haze and map the surface below, and it was that radar that revealed the lakes and seas, the rivers and dunes, the whole hidden world below. But Cassini did something even bolder than look. It brought a passenger. That passenger was a small European probe called Huygens, and on the 14th of January in the year 2005, it did something that had never been done before and has not been done since. It descended through Titan's thick orange atmosphere, parachuting down for more than 2 hours, sampling the air as it fell, and it landed softly on the surface of a moon of Saturn. It was the first landing ever accomplished in the outer solar system, more than 1 billion kilometers from the Sun, and for a short while before its batteries died in the cold, it sent back the view from the ground. The images showed a dim orange scene, rounded pebbles of water ice scattered across a damp plain, a place that looked eerily like a dry riverbed on Earth, shaped by the flow of a liquid that was not water. Somewhere out there, that little probe is still sitting, frozen and silent, the loneliest object humanity has ever placed on solid ground. I want you to try to stand there for a moment, because Titan rewards the imagination. Picture yourself on the shore of one of those seas, near Titan's pole, in the long, slow afternoon of a world where a single day lasts about 16 Earth days. The light is dim, a heavy amber twilight, because the thick haze overhead lets only a fraction of the distant sun's light reach the ground. The sun itself is a bright, blurred smear behind the orange, giving perhaps 1% of the daylight you know on Earth, so that even at noon it feels like the last hour before dusk. The air is thick around you, thick enough to feel, and bitterly cold, 94 Kelvin, cold enough to turn the gases of your own world to liquid and ice. In front of you a sea of liquid methane stretches to a flat horizon, utterly still, because Titan's winds are gentle and its gravity is low, so any waves would be slow, sluggish, glassy things. A soft rain of methane may have passed not long before, and every dark surface glistens with it. There is no sound but what you bring with you, and if you looked down at your feet, you would see that the ground beneath you is not soil or rock in any earthly sense. It is water ice as hard as granite, dusted and buried under a soft, dark layer of organic material that has been drifting down out of the sky for longer than there have been eyes to watch it fall. That soft, dark layer is the thing to remember as we go on, because it is in that organic sediment, that slow snow of complex molecules settling out of the haze, that the mystery fingerprint most likely hides. Titan has been running a chemical factory in its atmosphere for billions of years, taking simple nitrogen and methane and building them into something more elaborate, and then letting the products fall and gather on the ground. Whatever is absorbing light at 5.11 micrometers, the leading idea is that Titan's own sky has been manufacturing it, patiently, for ages, and laying it down across the surface like a fine dark dust. But Titan is only half of the puzzle. For this discovery to make sense, we have to explain why the same fingerprint shows up on a world that has almost none of Titan's advantages, a world with barely any atmosphere at all, far colder, far smaller, far away in the outer dark. We have to travel from a moon with seas and rain, and a nitrogen sky all the way out to the frozen edge of the planetary system, to the world we once called the 9th planet, and ask how it could possibly be wearing the same unknown thing on its face. Part 4. the world at the edge of the sun's reach. Pluto is a world that spent 70 years as a dot and then, in a single afternoon, became a place. For most of the time we knew about it, Pluto was almost nothing to us but a faint speck of light. It was discovered in the year 1930, a tiny moving point found on photographic plates by a young astronomer named Clyde Tombaugh, and for the next 85 years it stayed essentially that, a speck too small and too far to resolve into anything more. Even the finest telescopes could tease out only a blurred smudge, a few dark and light patches, nothing you could really call a surface. Pluto was less a world than a rumour at the edge of the map, the 9th name in a list most of us memorised as children, orbiting out in a region of the solar system so distant and so dim that sunlight there is a feeble thing. To understand how far away Pluto is, you have to stretch your sense of distance past the point where it stays comfortable. Pluto orbits the Sun at an average distance of about 39.5 astronomical units, where 1 astronomical unit is the distance from the Earth to the Sun. That means Pluto sits, on average, nearly 40 times farther from the Sun than we do, out in the cold beyond Neptune, in a region called the Kuiper Belt, a broad ring of icy bodies left over from the birth of the solar system. Out there, the Sun is no longer the great warm disk that rules our sky. It is a brilliant point, still the brightest thing around, but small enough that from Pluto you could nearly mistake it for an especially bright star. The sunlight that reaches Pluto is roughly 1,000 times fainter than the light we enjoy on Earth. Noon on Pluto is dimmer than a moonlit night at home, and it is cold there in a way that is hard to hold in the mind. The surface temperature on Pluto hovers around 40 Kelvin, which is about minus 230 degrees Celsius. That is cold enough to freeze gases that never come close to freezing on Earth. Nitrogen, the gas that makes up most of the air you're breathing, lies frozen solid across Pluto's surface. Methane and carbon monoxide are frozen there too. At 40 Kelvin, the ordinary rules of matter rearrange themselves, and substances we only ever meet as gases become the bedrock and the snow of an entire world. Pluto does have an atmosphere, but it is the faintest whisper of one, and this is the first great contrast with Titan. Where Titan's air presses down with more force than Earth's, Pluto's atmosphere is almost unimaginably thin. The pressure at Pluto's surface is around 1 Pascal, which is something like 100,000 times thinner than the air on Titan, and about that many times thinner than the air at Earth's sea level as well. It is close to a vacuum by our standards, and yet it is real, and it matters, because it is made of the same key ingredients as Titan's, nitrogen with a little methane and carbon monoxide mixed in. 2 worlds, one with a thick, heavy sky, and one with barely a breath of one, and both of those skies built from nitrogen and methane. Hold on to that, because it is the thread that will tie them together. Everything we truly know about Pluto's surface, we learned in a rush, on a single day in the summer of the year 2015. That was when a small, fast spacecraft called New Horizons, after a journey of 9.5 years and more than 4.5 billion kilometers, swept past Pluto at enormous speed, and in the space of a few hours transformed it from a smudge into a world. New Horizons could not stop. It was moving far too fast for that, and it simply flew through the Pluto system on the 14th of July, taking as many images and measurements as it could as the world rushed by. But those few hours were enough to overturn everything. The blurred speck became a place with mountains and plains, with glaciers and hazes, with a face more varied and more active than almost anyone had dared to predict. The most famous feature it found was an enormous pale rounded region, bright against the darker terrain around it, shaped a little like a broad valentine, that the whole world recognized instantly from the flyby images. Scientists named it Tombaugh Regio, after Pluto's discoverer, and the western half of that bright region turned out to be one of the most remarkable places in the solar system, a smooth, level plain of frozen nitrogen called Sputnik Planitia. This is not dead, ancient ice. Its surface is broken into enormous polygonal cells, the signature of slow-churning motion, nitrogen ice warmed ever so slightly from below and turning over like the surface of a simmering pot, except across tens of kilometers and over ages. It is a glacier of frozen air, alive with the slowest kind of movement, on a world we assumed would be frozen stiff and finished. Around it rise mountains of water ice, standing tall and sharp, because at Pluto's temperatures water ice is so hard it behaves like rock and can hold up peaks kilometers high. Then there is the colour. Parts of Pluto are stained a dark reddish-brown, most notably a shadowed region along its equator that scientists nicknamed Cthulhu, a long shadowy stretch quite unlike the bright nitrogen plains. That reddish material is the same family of substance we met on Titan. It is tholins, complex organic molecules built when sunlight and radiation work on methane and nitrogen, drifting down and colouring the ground. Even Pluto's thin atmosphere, New Horizons discovered, is layered with dozens of separate hazes, faint blue tears stacked one above another, catching the distant sunlight. On a world with almost no air, the same haze-making chemistry that shrouds Titan is quietly at work, painting Pluto red and hanging veils in its sky. There is a human story folded into Pluto's discovery that is worth pausing on. The young astronomer who found it, Clyde Tombaugh, was a farm boy from Kansas with no formal training, who had built his own telescopes from spare parts and sent his careful drawings of Jupiter and Mars to a professional observatory, which was impressed enough to offer him a job. His task there was grueling. He spent night after night photographing the same patches of sky days apart, then comparing the plates by flicking between them in a machine that made any moving object appear to jump back and forth while the fixed stars stayed still. He examined hundreds of thousands of star images this way for the better part of a year, until at last, in early 1930, one faint point jumped. That jump was Pluto. It was found by patience and eye strain, one flickering speck against a field of stars, by a young man who would live long enough to see it become a real world, and decades after his death to have a pinch of his ashes carried aboard the very spacecraft that flew past it. Pluto does not travel alone either. It has a large moon named Charon, so large relative to Pluto, more than half its width, that the two of them are almost a double world, swinging around a point in the empty space between them, rather than one simply circling the other. Around them wheel several smaller moons, and together they make up a miniature system out in the cold. And in the years since its discovery, we have learned that Pluto is not a lonely oddball at all, but the best-known member of a whole population of icy bodies beyond Neptune, the Kuiper Belt, thousands upon thousands of frozen worlds left over from the making of the solar system. That is really why Pluto was reclassified some years ago from a planet into a dwarf planet. It was not a demotion so much as a correction to our map. We realized Pluto was not the runt at the end of the planets, but the first discovered member of an enormous new territory, the nearest and brightest of a great swarm of worlds we had not known was there. Whatever you choose to call it, Pluto turned out to be a doorway into a whole unexplored region of the solar system. Let yourself stand there, too, the way we stood on Titan's shore, because the contrast is the whole point. You're on Sputnik Planitia now, in the middle of a plain of frozen nitrogen that runs to the horizon in every direction, flat and pale and faintly patterned with the outlines of those great slow cells. On the far edge, mountains of water ice rise like a wall, sharp and unmoving. There is no thick orange sky here to soften the light. The blackness of space comes almost all the way down to the ground, and hanging in that near-black sky is the sun, not a disk but a single searing point, so far away that it gives you 1,000th of the light you grew up under. Your shadow, if you can see it at all, is faint and thin. The cold is beyond anything words were built for, 40 Kelvin, cold enough to freeze the air of your homeworld into stone beneath your boots. Nothing moves, nothing sounds. The stillness is total and ancient, and yet you are standing on a glacier that is slowly, imperceptibly turning over, a surface being remade over timescales that make a human life not even a flicker. Pluto is the far shore of the sun's kingdom, the last lit place before the true outer dark, and it is quietly, stubbornly alive. What makes that plain of nitrogen ice so remarkable is that it should not, by any simple reckoning, be moving at all, and yet it is. The great polygonal cells that cover Sputnik Planitia are the surface signature of slow churning from below, nitrogen ice warmed just enough by the faint heat of Pluto's interior to rise in the centres of the cells, spread out, cool, and sink again at the edges, turning the whole plane over across timescales of perhaps 1,000,000 years for a single cycle. It is the same kind of motion you see in a pot of soup beginning to simmer, except drawn out to a stateliness that beggars the imagination and carried out in frozen air rather than hot liquid. A surface we assumed would be dead and ancient turns out to be constantly, if imperceptibly, renewing itself, which is why Sputnik Planitia has almost no craters at all. They are erased as fast as they form, swallowed by the slow churn, and there are strong hints that Pluto, like Titan, hides an ocean of liquid water far beneath its frozen shell, kept from freezing by the slow heat of its rocky interior and perhaps by antifreeze compounds dissolved within it. The very existence of Sputnik Planitia, its position on Pluto, and the pattern of stresses frozen into the crust all point toward a hidden sea, buried under 100 kilometers or more of ice. If that is right, then even here, at the cold edge of the sun's reach, on a world we long dismissed as a frozen relic, there may be liquid water sealed away in the dark, one of the classic ingredients we associate with the possibility of life. Pluto keeps refusing to be as simple, or as dead, as we expected. Even Pluto's thin atmosphere is not fixed. It swells and shrinks as Pluto's long orbit carries it nearer to and farther from the Sun, across its 2.5-century year, the frozen nitrogen turning to gas when the light strengthens and settling back onto the surface as frost when it fades. Pluto is a world that breathes, slowly, over centuries, its skin of frost and its wisp of air trading back and forth in time with its enormous orbit. This is the world, active and breathing and very possibly ocean-bearing, that wears the same unnamed fingerprint as Titan. Two worlds, then. One a giant moon with seas and rain and a heavy nitrogen sky. One a small, distant, half-frozen wanderer with barely any air at all, out where the sun is only a bright star. By almost every measure you could choose, they are opposites, and that is what makes the next fact so hard to shake off. Because in spite of everything that separates them, they are both marked at the same exact colour, with the same unknown thing. To understand how that could be, we have to stop looking at their differences and start looking at the one hidden thing they share. Part 5. Two Strangers, One Chemistry. The moment you stop asking how Titan and Pluto differ and start asking what they have in common, a pattern clicks into place that is almost too neat. On the surface, the comparison seems absurd. Titan is a giant moon. Pluto is a dwarf planet. Titan is more than 3 times wider than Pluto. Titan is drenched in a thick atmosphere. Pluto's is 100,000 times thinner. Titan has standing seas of liquid methane. Pluto's methane is frozen hard into the ground. Titan orbits Saturn, well inside the middle solar system. Pluto drifts far out in the Kuiper belt. If you were sorting worlds into families, you would put these two in different rooms and not think twice. But then you look at what their atmospheres are made of, and the differences start to feel like surface details over a shared skeleton. Titan's air is mostly nitrogen with methane mixed in. Pluto's air, thin as it is also mostly nitrogen with methane, and a little carbon monoxide besides. The proportions differ, the pressures differ enormously, but the essential recipe is the same. Both of these worlds are wrapped, thickly or faintly, in nitrogen and methane. And it turns out that this particular pairing of gases, when you leave it out in the cold and shine sunlight on it for long enough, does something remarkable and consequential. It refuses to sit still. Nitrogen and methane are both simple molecules. Nitrogen is 2 nitrogen atoms bound tightly together. Methane is a single carbon atom with 4 hydrogen atoms around it, the simplest of all the substances we call organic, meaning carbon-based. On their own, in the dark, they would do very little. But neither Titan nor Pluto sits in the dark. Sunlight reaches both, faint on Pluto but present, stronger on Titan, and beyond sunlight there is other energy at work, streams of charged particles, radiation from space, the constant low drizzle of the cosmos. When that energy strikes the nitrogen and the methane high in these atmospheres, it does something violent at the molecular scale. It breaks the molecules apart. It shatters methane into fragments, knocks pieces off nitrogen, and leaves behind a soup of reactive scraps, loose atoms and broken pieces desperate to bond with something. And bond they do. Those fragments recombine, not back into simple methane and nitrogen, but into larger, more elaborate molecules. A carbon here joins a carbon there. Nitrogen atoms work their way into the chains. Hydrogen comes and goes. Step by step, in countless tiny reactions, the chemistry builds upward, assembling heavier and more complicated organic molecules out of the wreckage of the simple ones. This process even has a name that captures its spirit. It is a kind of chemistry driven by light, and the products grow more complex the longer it runs. Given enough time, and both of these worlds have had billions of years, that upward building chemistry produces the tangled, heavy organic particles we keep calling tholins, the orange smog of Titan and the red stain of Pluto. This is the shared engine. This is the thing that two worlds so different in almost every other respect both possess. Each of them has a nitrogen and methane atmosphere. Each of them is bathed in enough energy to break those molecules apart, and each of them, as a result, runs the same slow factory in its sky, taking simple gases and manufacturing complex organic solids, which then drift downward and settle onto the surface below. Titan runs this factory at full industrial scale, cloaking itself in permanent haze and burying its surface under a thick organic layer. Pluto runs a fainter version of the same factory, thin haze and a lighter dusting, but the same chemistry all the same kind of molecules assembling by the same kind of steps. It is worth dwelling on why this particular pairing of gases is so productive, because it is not an accident that nitrogen and methane, of all things, are the ones building complexity. Methane is the simplest possible carbon-bearing molecule, a single carbon atom holding 4 hydrogens, and carbon is the one element in the universe with a genius for building. Carbon atoms can link to one another and to many other elements in long chains, in rings, in branching structures, forming an almost endless variety of molecules. That flexibility is the entire reason life on Earth is built from carbon rather than anything else. So when you break methane apart, you are releasing carbon fragments that are practically begging to build, and when you do it in an atmosphere full of nitrogen, those fragments start taking nitrogen atoms into their structures as well, which matters, because nitrogen is a key ingredient in the molecules of life, in proteins and in genetic material alike. This is also, and not by coincidence, thought to resemble the situation on the early Earth. Our own planet, in its youth, before there was oxygen in the air or life on its surface, very likely had an atmosphere heavy in nitrogen with methane and other simple carbon compounds mixed in, energized by an active young sun and by lightning. In other words, the early Earth may have been running a chemistry not so different from the one Titan runs today, building complex organics out of simple gases. That is part of why scientists are so drawn to these cold worlds. They are not merely curiosities, they are working models of a process that may have set the stage for life here, preserved and still running in slow motion, out where the cold keeps everything patient. Titan and Pluto are, in a real sense, 2 natural experiments in prebiotic chemistry, left running for billions of years without interruption, and the 5.11 micrometer signal is one of their results, sitting there waiting to be understood. There is one more reason the two-world nature of this discovery matters so much, and it is easy to overlook. If this fingerprint had turned up on Titan alone, it would still be a puzzle, but a smaller and more suspicious one. A single unexplained feature on a single world invites the worry that something local is fooling you, some peculiarity of that one place, some quirk in how we happen to observe it. But the same feature, at the same colour, on a second and very different world removes that worry almost entirely. 2 independent worlds do not conspire to fool you in the same way by accident. The repetition is itself a kind of proof, not of what the substance is, but of the fact that it is real, and that it is the product of something general, something not tied to the accidents of any one place. And that generality is the quiet headline of the whole discovery. It says that whatever makes this substance is not a Titan oddity or a Pluto oddity, but a process robust enough to run on 2 worlds that share almost nothing except the raw ingredients of nitrogen and methane and a source of energy. Give the universe those few simple things, apparently, and it will build this particular unnamed material, here in the middle solar system, and again out at its frozen edge, with no communication between the two. That is a strong hint that if we looked at other cold worlds with nitrogen and methane, we might find the very same fingerprint waiting there as well. The substance may not be a rarity at all. It may be one of the standard products of cold organic chemistry across the outer solar system, common as frost, and simply overlooked until an instrument sharp enough finally caught it in 2 places at once. So the shared signal is not a coincidence to be explained away. It is the most important clue we have. It tells us the mystery is not local, but general, not fragile, but robust, and that somewhere in the ordinary chemistry of cold nitrogen and methane worlds is a recipe we have not yet written down, producing a substance we have not yet named, reliably enough to mark 2 separate worlds with the same quiet signature. Once you see that, the mystery reorganizes itself. It stops being a bizarre coincidence, 2 unrelated worlds happening to share an impossible feature, and it starts being something almost expected. If both worlds are running the same chemistry, why should we be surprised that they produce among all their products at least one substance in common? The 5.11 micrometer fingerprint may simply be one of the things this shared factory makes. A particular molecule, or a particular mixture, that arises naturally when you take nitrogen and methane and process them with light and radiation over ages, laid down on Titan and laid down on Pluto by the same fundamental recipe. The two worlds do not need to have touched or traded material or shared a history. They only need to be running the same machine. And they are. That is a genuinely satisfying idea, and it is the leading explanation among the scientists who study these worlds. But notice what it does and does not do. It gives us a reason for the coincidence. It explains why the same signal could appear on two such different worlds. What it does not do is tell us what the substance actually is. Knowing that a factory made something is not the same as knowing what came off the line. We have identified the engine without identifying the product, and when the researchers went looking for exactly which product this might be, exactly which molecule the shared chemistry had assembled to leave that fingerprint at 5.11 micrometers, they ran straight back into the wall we started with. Because whatever it is, it still matches nothing we have on file. Before we go hunting through the short list of suspects, though, it is worth slowing down and watching the factory at work. Because the way these organic molecules are born, high in a cold sky, and the way they fall is one of the strangest and most quietly beautiful processes in the solar system, and it is happening on both of these worlds right now, in the dark, whether or not anyone is watching. Part 6. The snow that falls in the dark. There is a kind of snow that falls on Titan and Pluto that has nothing to do with water, and once you understand where it comes from, you will never think of these worlds as empty again. To watch it form, you have to go up, high above the surface, to the top of the atmosphere where the sunlight is strongest and the air is thinnest. This is where the factory floor is. Here, molecules of nitrogen and methane are drifting in the cold, and here the energy arrives, ultraviolet light from the distant sun, charged particles guided in along magnetic field lines, the steady radiation of space. When that energy strikes a methane molecule, the molecule cannot simply absorb the blow. The energy is enough to break its bonds, to tear a hydrogen atom loose, to split the tidy little structure into reactive pieces. The same happens to nitrogen, though nitrogen is tougher and holds together harder. Suddenly the calm upper air is full of fragments, chemically hungry, and they begin to find each other. What follows is not a single reaction, but a slow cascade of thousands, a chemistry that builds patiently upward. 2 carbon fragments join to make a molecule with 2 carbon atoms. That molecule meets another piece and grows to 3, to 4. Chains lengthen, rings close, nitrogen atoms weave themselves into the growing structures. With every step the molecules become larger, heavier, more intricate, and less like the simple gases they started as. This is the ladder of organic chemistry being climbed in the open air of an alien sky, rung by rung, each product becoming the raw material for something more complex still. And because the process runs on light and never truly stops, it has been climbing that ladder for as long as these worlds have had atmospheres, which is to say for billions of years. Eventually the molecules grow too large and too heavy to remain gases. They begin to clump together into tiny solid particles, specks of tangled organic matter suspended in the air. These are the tholins, and they are what we see as the haze. On Titan they are so abundant that they form a thick layered smog that turns the whole moon orange and hides its surface completely. On Pluto they are thinner, forming those faint blue tears New Horizons photographed hanging in the sky. The word for these dark organic particles is worth knowing, because it carries a small confession inside it. They are called tholins, a name coined by the astronomer Carl Sagan and a colleague in the late 1970s when they were producing exactly this kind of material in their laboratory by energizing mixtures of gases like those on Titan. When they made the stuff, they found it was not a single clean compound they could easily name, but a brown, sticky, tarry tangle of many organic molecules mixed together, so they reached for a Greek word meaning muddy and called the product tholins. The name itself admits that this material is a mixture, a muddle, something that resists being pinned down to a single formula. That admission is worth holding on to because it is exactly the quality that makes our mystery so hard to solve. Tholins are, by their very nature, not one thing. In the laboratory, tholins come out as a reddish-brown residue coating the inside of the apparatus, and their colour is the same colour we see staining Pluto and tinting Titan's haze. That is a satisfying confirmation. We can make, on a bench, the very material that colours these distant worlds, which tells us we understand the broad process even where we cannot name every product of it. Tholins are not a single molecule, but a whole family of organic substances, built by energy working on simple gases, sticky and complex and chemically restless. Give them water and a little warmth and they begin, in experiments, to yield the building blocks of biology. And they are precisely the kind of material that could hold, somewhere within their tangle, the substance that absorbs light at 5.11 micrometers. When the researchers suggest that our mystery is probably not a pure compound but a complex mixture, they are describing something very much like a tholin, a muddle of organics assembled by nature that no single page of our clean, one substance at a time catalogue was ever going to match. But once a particle has grown heavy enough, gravity takes over, and it begins the long, slow fall toward the ground. This is the snow. Not white, not cold crystals of water, but dark grains of complex organic material, sifting down out of the haze, drifting through the thin, cold air over months and years, settling at last onto the surface below. It is worth pausing on how slow and how old this process is, because the timescales are part of what makes it hard to hold in the mind. A single organic particle, born high in the haze, may take months or even years to complete its fall to the ground, sinking through the cold air with almost no weight to hurry it. And the falling has been going on, without interruption, for a very long time. Titan has had its thick atmosphere and its haze for a good fraction of the age of the solar system, which means this snow has been settling for hundreds of millions of years at the very least, quite possibly for billions. Layer upon layer, grain upon grain, it has built the organic blanket that now covers the moon, a sediment of the sky's slow chemistry, gathered over spans of time that dwarf the whole history of life on Earth. That is why the deposits can be so substantial. When you let even a fine snow fall for hundreds of millions of years, it adds up. On Titan, the organic layer may reach a metre or more in places, filling the dunes and mantling the plains, a genuine geological unit made entirely of fallen chemistry. The mystery substance we are chasing is somewhere in that accumulation, and it too has been gathering for ages, which means that when we finally identify it, we will be identifying something with a very long past, a material that has been quietly assembling and settling since before there were creatures on Earth to wonder about anything at all. There is a particular kind of patience in that image that I find worth holding. The snow does not know we are watching. It did not begin falling for our benefit, and it will not stop when we finally name it. It is simply the slow exhaust of a planetary chemistry that has been running, untended, for eons, and we have arrived at one brief moment in that immense span, pointed an instrument at the result, and noticed something we cannot explain. The snow will go on falling in the dark long after this mystery is solved, adding new layers to a record that no one reads, on two worlds that keep their own quiet time. Come and watch it happen, because it is worth seeing in the mind's eye. You're standing on Titan again, in the amber twilight, and you look up into the haze. You cannot see the individual particles being born far above you, but you know they are there, sunlight quietly stitching nitrogen and methane into something heavier with every passing moment. What you can see, if you are patient and still, is the result. The air itself seems faintly, endlessly full, a slow descent of dark motes too fine to track, drifting down through the thick atmosphere without hurry, because Titan's gravity is gentle and its air is dense and nothing here falls fast. It is snowing, in a sense, and it has been snowing like this since before the first life stirred on Earth. The grains settle on the ice at your feet, one on top of another, over centuries, over ages, building a soft, dark blanket across the whole world. In places that blanket of organic snow may be only centimetres thick. In others it may reach a metre or more, a fluffy, sooty layer lying over the hard water ice beneath. You're watching a world slowly bury itself in the products of its own sky. And now the thought that should stop you where you stand. This same snow, this same dark organic settling, is happening at the same time on Pluto, billions of kilometres away, out where the sun is only a bright point. Fainter there, thinner, slower, but the same. Two worlds that have never touched, that formed in different regions, that have never in the history of the solar system exchanged so much as a single atom, are both, right now, in the dark and unwatched, laying down the same kind of organic material by the same patient process. It is as if the universe wrote the same word twice, in two places impossibly far apart, in a hand we can almost but not quite read. There is no messenger between them, no shared cause reaching from one to the other. There is only the same physics, the same chemistry, running independently in two lonely places and arriving both times at the same result. That is not a coincidence in the ordinary sense. It is a pattern, and a pattern with no author is somehow more haunting than one with a hand behind it. That shared snow is almost certainly where our mystery lives. Somewhere in that slow-settling organic material on both worlds is the substance absorbing sunlight at 5.11 micrometers. It is not exotic in the sense of breaking any law. It is a product of the most ordinary process these worlds have, the same haze-making, snow-falling chemistry we have just watched. But it is a product we have not yet managed to name, a specific molecule or mixture assembled out there under conditions we have not reproduced in any laboratory, lying now across two surfaces as a fingerprint we can measure but cannot yet match. So the question sharpens. We know where to look. We know the substance is in the organic snow, made by the shared factory, deposited on both worlds. Now we have to ask which molecule it is. And to do that, the scientists did the natural thing. They gathered the short list of everything that could plausibly absorb light at exactly that colour, every candidate the chemistry could reasonably produce, and they held each one up against the fingerprint to see if it would fit. What happened next is the strange and frustrating centre of this whole story, because the suspects were all reasonable, and not one of them was right. Part 7. The search through every molecule we know. When you know a fingerprint is real, but no name comes up in the archive, the honest next step is to start guessing, carefully, and the guesses themselves tell you a great deal. The scientists did not throw up their hands. The exact position of an absorption feature is not arbitrary. It is set by the physics of chemical bonds, and that gives you clues about the kind of molecule you're dealing with even before you know the molecule itself. The colour of this feature, 5.11 micrometers, corresponds to a particular region of the infrared that chemists know well. It is the neighbourhood where you find a specific and somewhat unusual kind of chemical bond called accumulated double bond. That is a mouthful, but the idea behind it is simple and worth having, because it narrows the field. Most organic molecules are built from single bonds and here and there a double bond where two atoms share their connection more tightly. Accumulated double bond is a rarer arrangement, where a single central atom is caught between two double bonds at once, double bonded on both sides. Picture three atoms in a row, and the middle one holding a double bond to each of its neighbours. That configuration vibrates at a very particular frequency, and that frequency lands right around the colour we are chasing. So the feature is quietly telling us something about its source. Whatever is absorbing this light most likely contains one of these cumulated double bonds. That single clue is what shapes the entire short list of suspects. The first and most promising suspects are a family of molecules called allenes. An allene is exactly the kind of structure that region of the spectrum points to. A 3-carbon molecule with that cumulated double bond running through its middle, the simplest version being a compound called propadiene. Allenes are among the very few organic substances that naturally absorb light right around 5.11 micrometers, which makes them the best structural fit on paper. If you were betting purely on chemistry, you would put your money here. And yet, when the researchers compared the actual measured allene spectra they had against the fingerprint from Titan and Pluto, the match was close but not clean. The position was in the right neighbourhood, but not exactly on the mark. Promising, suggestive, and still not quite it. The second suspect is benzene, a molecule you may have heard of, a ring of 6 carbon atoms that is one of the most fundamental building blocks in all of organic chemistry. Benzene has a point in its favour that the others lack. We already know it is there. Benzene has been detected in Titan's atmosphere directly, so it is not a stretch to imagine it on the surface. The problem is that pure benzene, measured on its own, does not produce a fingerprint at the right place. On its own, benzene is ruled out, but chemistry is rarely pure. When you mix benzene with other substances, when its molecules sit crowded among different neighbours, the exact positions of its absorption features can shift. So the idea on the table is not pure benzene but benzene combined with something else. A mixture whose merged fingerprint might land where we see the mystery signal. It is a maybe, dependent on exactly what it is mixed with, and that dependence is part of why it stays unproven. The third suspect is a molecule called ketene, which also carries one of those cumulated double bonds, in its case between 2 carbons and an oxygen. Ketene absorbs near the right colour, which keeps it on the list. And interestingly, when other researchers have taken simple ices, things like frozen methanol, and bombarded them with radiation to see what forms, the processed material shows features not far from this position. That hints at a whole class of possibilities, substances forged by radiation working on simple ices, producing something that absorbs near 5.11 micrometers. Ketene itself, or something in its family, cannot be dismissed. And then there is a fourth suspect, considered less likely but not impossible, a molecule called acetylene, 2 carbons joined by a triple bond, a substance also known to exist on Titan. On its own it does not fit well, but again, in a processed or mixed form, under the right conditions it lingers at the edges of the list. So there is the lineup. Alanies, the best structural match but not exact. Benzene, present and plausible, but only in a mixture. Ketene and its radiation-forged relatives, absorbing in the right place but unconfirmed. Acetylene, a long shot. 4 reasonable candidates, every one of them a genuine possibility, and not a single one of them a clean, confident match to the fingerprint. The archive is still empty, the name is still missing. This is where the phrase from the beginning of the night hardens into something literal, a fingerprint that belongs to nothing. When we first said it, it was almost a figure of speech, a dramatic way of describing a signal without a match. But after the search, after holding up every reasonable candidate and watching each one fall just short, the phrase becomes plain fact. This is a fingerprint that so far genuinely belongs to none of the substances we can name. The lead researcher on the study put the situation in a way that is both humble and quietly thrilling. Whatever this turns out to be, he suggested, it is going to be a surprise, and the most likely reason no single candidate fits is that the answer is not a single substance at all. It is probably a complex mixture, several organic materials tangled together, producing a combined fingerprint that no one pure compound in our library could ever reproduce on its own. That idea deserves a moment, because it reframes the failure as a kind of message. Perhaps the reason our archive has no page for this is that our archive is built mostly from pure substances, carefully measured one at a time, and nature out on these worlds does not work in pure substances. It works in mixtures, in messy accumulated sediments built over ages, in combinations we have never thought to prepare and measure. If that is true, then the mystery is not pointing at some strange new element or impossible compound. It is pointing at the limits of how we have chosen to study chemistry, at the gap between our clean laboratory catalogue and the tangled reality of a world burying itself in organic snow. The substance is not hiding from physics. It is hiding in the difference between how we catalogue matter and how the universe actually assembles it. If the idea of a fingerprint that matches nothing still sounds alarming, it helps to know that this has happened before in the history of astronomy, more than once, and every time it turned out to be a door rather than a wall. In the middle of the 1800s, when astronomers first studied the light of the sun during an eclipse, they found a bright line at a colour that matched no known element on Earth. Rather than assume it was impossible, they gave the unknown source a name, helium, after the Greek word for the sun, and accepted that there was apparently an element in the sun that had never been found here. Nearly 30 years passed before helium was finally isolated on Earth and its identity confirmed. For a generation, helium was quite literally a fingerprint that belonged to nothing in our catalogue, known only from sunlight, and it was real the whole time. The same thing happened twice more. When astronomers studied the glowing gas of distant nebulae, they found bright lines that matched nothing known, and for decades people spoke of a mysterious substance they called nebulium, imagined to exist only out in those clouds. And when they studied the faint outer atmosphere of the sun, its corona, they found still other lines with no match, and invented another phantom, coronium. Both of these turned out, in the end, not to be new elements at all, but familiar ones, oxygen and iron, in extreme and unusual states we had simply never produced or measured in a laboratory. The lines were real. The interpretation had a gap, and the gap was filled not by discovering some impossible new substance, but by realizing that ordinary matter, under conditions we had not reproduced, could produce fingerprints we had never seen. That is almost certainly the situation we are in now with the 5.11 micrometer feature. It is very likely not some impossible new kind of matter. It is far more likely to be ordinary organic chemistry, familiar atoms in a particular arrangement or a particular mixture, produced under the cold and irradiated conditions of these worlds, conditions we have not yet fully recreated on a bench. The history of this science is, in large part, a history of fingerprints that belonged to nothing until, patiently, we learned what they belonged to. Helium, nebulium, coronium, each one a temporary mystery that dissolved into knowledge. There is every reason to expect this new one will follow the same path, and every reason to enjoy the interval before it does, because we are living right now in the brief window while the answer is still unknown. There is one more clue we have not used yet, and it may be the most revealing of all. Because the fingerprint is not quite identical on the two worlds. It sits at the same colour, yes, but it does not have the same shape, and that difference, narrow on one world and broad on the other, turns out to be a mystery folded inside the mystery. Part 8. Why the same signal wears two faces. The most intriguing detail in the whole discovery is not that the two fingerprints match, but the one small way in which they do not. When the researchers measured the feature carefully on each world, they found that the centre sits at the same colour on both, matching to within the precision of their instruments. That is the part that ties Titan and Pluto together, but the width of the feature, how broad or narrow the valley is not the same. On Titan, the feature is comparatively narrow, a well-defined notch with sharply measured edges. On Pluto, the feature at the very same colour is roughly 3 times broader, a wider and softer valley. Same position, different shape. The universe wrote the same word on both worlds, but in one place the handwriting is crisp and in the other it is smeared. At first, that might sound like a problem for the whole idea. If the shapes differ, are we even sure it is the same substance? But in the science of spectra, a difference in width without a difference in position is not a contradiction. It is a clue about the physical state of the material, rather than its chemical identity. The position of a feature tells you what the molecule is, because it is set by the bonds. The width tells you about the conditions the molecule is living in, how it is packed, how ordered or disordered its surroundings are, how it has been treated. The same substance can show a narrow feature in one setting and a broad one in another, depending on what has happened to it. So the width difference is not evidence against a shared compound. It is evidence about the different lives that compound is leading on the two worlds. There are a few ways to explain why Pluto's version would be broader, and they are not mutually exclusive. The truth may be some combination of all of them. The first and most compelling has to do with the thing we already know sets these worlds apart, their atmospheres. Titan is wrapped in a thick, heavy sky, and that sky is a shield. It absorbs and deflects much of the radiation and the energetic particles that come streaming in from space, so the organic material lying on Titan's surface is relatively protected, cushioned beneath more than 1 billion tons of atmosphere. Pluto has almost no such shield. Its atmosphere is 100,000 times thinner, close to nothing, and so the surface of Pluto is far more exposed to the constant bombardment of cosmic rays and radiation from space. That bombardment matters, because radiation does not leave organic molecules untouched. When high-energy particles strike a molecule, they can break its bonds, knock atoms loose, and rearrange its structure. Spread that over a whole surface exposed for ages, and you get a population of molecules that has been battered and processed, some intact, some broken, some reformed into slightly different configurations. A collection like that, a range of molecules in varying states of damage, absorbs light over a slightly wider spread of colours than a clean, uniform protected population would. The result is a broader feature. So the very thing that makes Pluto so different from Titan, its lack of atmosphere, could be exactly what smears its version of the fingerprint. On Titan, the substance is sheltered and orderly, and its feature is narrow. On Pluto, the same substance is exposed and worked over by radiation, and its feature is broad. The difference in width becomes a record of the difference in shelter. The second explanation is simpler and more physical. It has to do with grain size. The organic material on these surfaces is not a smooth sheet. It is made of grains, tiny particles piled together, and the size of those grains affects how light interacts with them. Larger grains and smaller grains scatter and absorb light a little differently, and can subtly change the apparent width of a feature. If the organic snow on Pluto has settled into grains of a different typical size than on Titan, perhaps because it falls through a thinner atmosphere, perhaps because of the different temperatures, that alone could account for some of the broadening. The chemistry would be identical, only the texture of the deposit would differ. The third explanation is about company. A molecule embedded in one kind of surrounding material behaves a little differently than the same molecule surrounded by another. On Titan, the The mystery substance sits amid one particular mix of organic sediment and ice. On Pluto, it sits amid frozen nitrogen, frozen methane, frozen carbon monoxide, and reddish tholins, a different set of neighbours. Those different surroundings can nudge and spread a feature, shifting its shape without moving its centre. The substance is the same, the crowd it stands in is different, and the crowd leaves its mark on the fingerprint. Notice what all three explanations have in common. Every one of them keeps the substance itself the same on both worlds, and blames the difference in width on circumstance, on radiation, on grain size, on surroundings. That is a strong and consistent story. It says the same compound is present on Titan and Pluto, but it is living two different lives, sheltered and orderly on one world, exposed and battered on the other, and the shape of the fingerprint is quietly reporting the difference. There is something almost poignant in that. The same material, born of the same chemistry, laid down on two worlds by the same falling snow, and then shaped by the specific hardships of each place, so that even its signature carries the memory of where it has been. To feel why the width of a feature tells you about physical state, it helps to think about the difference between a substance that is neatly ordered and one that is jumbled. When molecules are locked into a clean, regular crystal, each one sits in nearly the same setting as its neighbours, feeling the same forces, vibrating at nearly the same frequency. Because they all absorb at almost exactly the same colour, the resulting feature is narrow and sharp, a chorus singing precisely in tune. But when the same molecules are packed into a disordered glassy jumble, each one sits in a slightly different setting, squeezed and tugged in slightly different ways, so each absorbs at a slightly different colour. The feature spreads out into a broader valley, a chorus singing the same note but slightly out of tune with itself. Width, in other words, is a measure of disorder and disturbance. A narrow feature means a calm, ordered, undisturbed material. A broad one means a material that has been jumbled, processed, or knocked out of alignment. Seen that way, the difference between Titan and Pluto tells a story about their surfaces. On Titan, sheltered under a thick atmosphere, the mystery substance appears relatively ordered, its feature narrow, as though it has been left in peace. On Pluto, exposed to the raw radiation of space, the same substance appears more disordered, its feature broad, as though it has been worked over and knocked about for a long time. Temperature can play a part too, since colder or warmer surroundings change how tightly molecules are held and how freely they vibrate. And so can the simple passage of time under bombardment, which slowly converts neat molecules into a battered mix. Every one of these effects points the same way. The substance on Pluto has had a harder life, and the broader shape of its fingerprint is the visible record of that hardship, written into the light for anyone who knows how to read the width as well as the position. But all of this, elegant as it is, still circles the same unanswered question. We can explain why the feature is broad here and narrow there. We can explain why it appears on both worlds at all. We simply cannot say what it is. And that unanswered question would be interesting enough on its own, a puzzle for the chemist to chew on. What lifts it into something that matters, something worth caring about far beyond the small community of scientists who study these worlds, is what these particular molecules represent. Because the substances on our shortlist are not random. They belong to the exact family of chemistry that, on one world at least, once led to something extraordinary. Part 9. The chemistry that comes before life. The reason a nameless smudge of organic material on two frozen worlds deserves your attention has to do with the oldest question we have ever asked, which is where we came from. Every candidate on the shortlist, and the whole tangled family of organic molecules being manufactured in the skies of Titan and Pluto, belongs to a branch of chemistry we call organic chemistry, the chemistry of carbon. It is the same chemistry that living things are built from. Your body, every cell in it, is an arrangement of organic molecules, carbon chains and rings decorated with hydrogen and oxygen and nitrogen, assembled into proteins and fats and the long spirals of your genetic code. When we talk about the search for life beyond Earth, at bottom we are talking about the search for this chemistry, carbon-based molecules complex enough to begin doing the things that lead, eventually, toward life. And Titan, of all the worlds in the solar system, is perhaps the greatest natural laboratory of that chemistry we have ever found. It is running, at planetary scale and over billions of years, the very process that scientists believe preceded life on Earth. Consider what we know about our own beginnings. Life did not appear on Earth fully formed. Before there were living cells, there was a long era of chemistry, in which simple molecules in the young Earth's air and oceans were energized by sunlight and lightning and heat, and slowly built themselves into more complex organic compounds. Amino acids, the building blocks of proteins, the components of genetic material. This is called prebiotic chemistry, the chemistry that comes before biology, and it is the bridge across which non-living matter first stumbled toward life. We cannot watch it on Earth anymore, because our planet's surface has been remade 1,000 times over, and life itself has erased the evidence of its own prologue. But we can watch something very like it on Titan right now. Titan takes nitrogen and methane and, using energy, builds them into steadily more complex organic molecules, exactly the kind of upward-building chemistry that must have run on the early Earth. Among the products of Titan's atmosphere is a molecule called hydrogen cyanide, which sounds sinister, but is one of the most important prebiotic molecules we know, a substance that in the right conditions can react and combine toward the building blocks of life. Titan is manufacturing prebiotic chemistry in its sky and raining it onto its surface. And there is water there too, locked as ice, but liquid in places most likely, when a comet strike or the moon's internal warmth melts the crust for a time. Mix Titan's organic snow with liquid water, even briefly, and you have something close to the conditions in which our own chemistry may have taken its first steps. Laboratory experiments that recreate Titan's tholins and add water have produced amino acids and other building blocks right there on the bench. We have actually tested this idea that simple gases and energy can build the parts of life, and the test is one of the most famous experiments of the 20th century. In 1952, a young researcher named Stanley Miller, working with the chemist Harold Urey, sealed a mixture of simple gases thought to resemble the early Earth's atmosphere into a glass apparatus, added water to play the part of the oceans, and ran electric sparks through it to stand in for lightning. He let it run for days, and when he analyzed what had formed, he found amino acids, the building blocks of proteins, assembled out of nothing but simple gases, water, and energy. It was a stunning result. It suggested that the raw materials of life are not rare or difficult, but form readily wherever you have the right simple ingredients and a source of energy to drive them. The chemistry that leads toward life may be, in a sense, eager to happen. Since then, we have found the same kinds of molecules in places we did not put them. Certain meteorites that fall to Earth, ancient rocks left over from the birth of the solar system, have been found to carry amino acids and even components of genetic material, formed out in space long before they arrived. The building blocks of life, it seems, are scattered widely, assembling on their own in many settings across the cosmos. And this is exactly why the cold worlds matter so much. If the ingredients of life form easily even in warm, wet, forgiving places like the young Earth, then the harder and more interesting question is how far that same chemistry can climb in the cold and the dark, on a world with no warm ocean, where the sun is faint and the temperatures are brutal. Titan is the great test of that question. It is building complex organics at industrial scale in conditions that could hardly be less like the early Earth, and by studying what it produces, including this very substance we cannot yet name, we get to measure just how universal and how stubborn the chemistry of complexity really is. Every unnamed organic on Titan's surface is a clue to whether the road toward life is a rare accident or a common tendency of matter itself. This is why Titan sits so high on the list of places we most want to search for signs of life, or at least for the chemistry that precedes it. It is not that anyone expects to find creatures swimming in its methane seas. The surface is far too cold for the chemistry of life as we know it to run at any useful pace. The interest lies in two places. First, in the surface chemistry itself, the organic material built by the atmosphere, which lets us study prebiotic chemistry running at planetary scale and over ages. And second, in that hidden ocean of liquid water far below the ice, where temperatures are much kinder and where, if organic material from the surface can somehow work its way down, the ingredients and the conditions for interesting chemistry might exist together. Titan may be two experiments in one, a frozen organic factory on top and a liquid water ocean beneath. Titan is not alone in this new way of thinking either. Over the past few decades, we have come to realize that the outer solar system is full of ocean worlds, moons with liquid water hidden beneath their frozen shells. Saturn's small moon, Enceladus, actually sprays its ocean into space through cracks near its south pole, and when spacecraft flew through those plumes, they found not just water, but salts and organic molecules, the chemistry of a possibly habitable place vented straight into the open where we could sample it. Jupiter's moon, Europa, is thought to hide an ocean holding more water than all of Earth's seas combined. Suddenly, the question of a life beyond Earth is not only about warm, rocky planets close to their stars, but about these cold, dark, ice-covered moons, where liquid water and organic chemistry may quietly keep company far from the Sun. The mystery substance on Titan and Pluto is a small piece of this much larger picture, but it is a real one. Every time we identify a new organic material on these worlds, we sharpen our sense of what chemistry can do in the cold and the dark, and of how ready the universe is to assemble the parts that matter. A dip in the light at 5.11 micrometers is, in the end, a question about ourselves, about how ordinary and how likely the road from simple chemistry to living things really is. So when we find an unidentified organic substance coating Titan's surface, and the same substance on Pluto, we are not just filling a gap in a chemistry catalogue. We are looking at the products of the exact kind of chemistry that, on our world, once led to us. We are looking at how far that chemistry can climb on a cold world with no life to guide it, how complex the molecules can get on their own, purely through sunlight and radiation and time. Every new substance we identify in that organic snow is a data point in the largest question there is. How readily does dead chemistry build the parts of life? Does it happen only in warm, wet, forgiving places like the early Earth? Or does it happen even in the frozen dark on a moon where the rivers are methane and the sun is a smudge? Titan is where we get to find out. And here is the thought I keep returning to, the one that gives this whole quiet discovery its weight. The molecules on our shortlist, the alkenes and the benzene and the ketene and whatever mixture they truly form, are the building blocks of the chemistry that came before life. On a frozen moon of Saturn, and on a dwarf planet at the edge of the sun's reach, we may be looking directly at a page from our own prologue, the early chemistry of a living world written out in cold organic snow. And we cannot read it. We have found the page, we can measure the shapes of the letters precisely enough to know they are really there, and we cannot yet make out a single word. There is something humbling in that, standing so close to a piece of the story of our own origins and being unable, for now, to say what it says. That is what turns a small dip in a spectrum into something worth 2 hours of your attention. Not the fear that it shouldn't exist, but the recognition of what it might be and what it might teach us about the road from lifeless chemistry to living things. It means the stakes of naming this substance are not merely academic. They touch the question of how common the ingredients of life really are, scattered across even the coldest and most unpromising corners of the solar system. Of course, wanting to know is not the same as being able to find out from here. There is a limit to what even the finest telescope can tell us across billions of kilometers. To truly read the page, we may have to do something far more ambitious than look. We may have to go to send a machine down through that orange haze and set it on the organic snow itself and let it take the substance in its hands. And remarkably, that is exactly what we are about to do. Part 10. The machine we are sending into the haze. We are not going to be content for much longer to study this mystery from across the solar system, because a machine is already being built to go and touch it. Its name is Dragonfly, and it is one of the most audacious spacecraft ever designed. For every previous mission to another world's surface, we have sent landers that stay put, or rovers that crawl slowly across the ground. Dragonfly is neither. It is a flying machine, a rotorcraft, a nuclear-powered drone about the size of a small car, carried aloft by 8 spinning rotors arranged in pairs. It is going to fly through the skies of Titan, and it can do this precisely because of the very thing that makes Titan so strange, its thick atmosphere and its low gravity. In air denser than Earth's, under gravity far weaker than ours, flying is actually easier on Titan than almost anywhere else in the solar system. A machine that would struggle to lift off here can hop for kilometers there on a single flight. Titan, the hardest world to see, turns out to be one of the easiest worlds to fly. Dragonfly will not run on sunlight, because sunlight on Titan is too feeble to power much of anything. Instead, it carries a nuclear core, a generator that turns the heat of slowly decaying radioactive material into a steady trickle of electricity. The same kind of power source that has kept our Mars rovers alive for years. That power will let it operate through Titan's long dark days, recharge between flights, and keep its instruments warm against a cold that would freeze ordinary electronics solid. And the plan is not to visit a single spot, but to leap from place to place across the surface, flying up to several kilometers at a time, landing, studying and flying on again, exploring a whole region of Titan over a mission expected to last several years. The place it is going is chosen with real care, and it matters for our story. Dragonfly will aim for a region called Shangri-La, an area of dark dunes near Titan's equator, and it will work its way toward a feature called Selk Crater. A crater is an interesting target for a specific reason. When something strikes a world hard enough to blast out a crater, it delivers a burst of heat, and on Titan that heat can melt the water ice for a while, creating pools of liquid water mixed with the organic material of the surface. That combination, liquid water plus complex organics, even if it lasted only a short time long ago, is exactly the recipe that interests anyone asking how chemistry becomes biology. Selk Crater is a place where Titan's organic snow and its buried water may once have met, and Dragonfly is going there to sample what that meeting produced. To do the sampling, Dragonfly carries an instrument that is, in a sense, the whole point. It is a mass spectrometer, a device that can take a pinch of surface material, break it apart and weigh the pieces with such precision that it can identify the molecules present. A telescope reads a substance's fingerprint from afar and hopes to match it. A mass spectrometer holds the substance in its hands and reads its composition directly. If Dragonfly lands on Titan's organic snow, scoops up a sample, and runs it through that instrument, it may be able to do what no telescope ever could. It may be able to name the substance behind the 5.11 micrometer fingerprint, not by guessing at a match, but by measuring the thing itself. To grasp how bold Dragonfly really is, it helps to compare it to everything that came before. Every craft we have ever landed on another world has been, in essence, fixed where it touched down, or able only to crawl. The landers on Mars sit in one spot for their entire lives. The rovers, remarkable as they are, creep across the surface at the pace of a slow walk, covering a handful of kilometers over many years, picking their way carefully around every rock and slope. A flying machine changes everything. In a single flight lasting less than an hour, Dragonfly can cover more ground than a Mars rover manages in its whole mission, leaping over terrain that would stop a wheeled craft cold, choosing entirely new sites from the air. It turns exploration from a crawl into a series of hops, and it means that across its mission, Dragonfly can sample many different places on Titan, not just the one where it happened to arrive. It carries more than the one instrument too. Alongside the mass spectrometer that will read the composition of the surface, it has cameras to scout the terrain and study the ground beneath it, sensors to measure the weather and the properties of the air, a device to examine the surface material where it sits, and instruments to listen for the faint tremors of the moon, which could reveal the hidden ocean far below. Each landing site becomes a small field station where the craft studies the air, the ground, the chemistry, and the interior before folding up its findings and flying on to the next. Over the course of the mission, it will build a portrait of Titan not from a single point, but from a whole scattered survey, tracing how the organic material changes from place to place, which is exactly the kind of information needed to understand where our mystery substance forms and why. And the choice to fly is not a gimmick. It is the natural response to what Titan is. On a world with an atmosphere thicker than Earth's and gravity far weaker, wings and rotors work beautifully, better than they do at home. The same thick haze that hid Titan's face for centuries, the same dense cold air, is the very thing that makes flight there so easy. There is a quiet symmetry in that. The atmosphere that has kept Titan's secrets is the atmosphere that will let us fly through it to uncover them. And when Dragonfly finally reads the composition of the organic snow directly, when its mass spectrometer weighs the molecules that a telescope could only guess at from 1 billion kilometers away, it may at last close the gap between the fingerprint and the name. The timeline is real, and it is set. Dragonfly is scheduled to launch in the summer of the year 2028, riding a powerful rocket up off the Earth. Then comes the long crossing, roughly 6 years of coasting through the solar system, until it arrives at Titan in the year 2034. The machine has already passed the major review that clears it for full construction, so it is no longer just a concept on paper, it is being built. Sometime in the middle of the next decade, if all goes well, a nuclear-powered drone will spread its rotors in the thick orange air of a moon of Saturn and begin to fly. The journey itself is worth dwelling on, because it is a reminder of how much patience these missions demand. The distance to Saturn is so great that even a fast spacecraft, launched with all the energy we can give it, needs several years to cross it. Dragonfly will spend roughly 6 years in transit, coasting silently through the solar system while the people who built it wait and watch and prepare. Many of the scientists and engineers who launch it will spend a meaningful stretch of their careers simply waiting for it to arrive. There is a kind of generosity built into a mission like this, a willingness to begin something whose reward will not come for a decade or more, to send a machine toward a distant goal and trust that the patience will be repaid. It is the same patience, in a way, that the snow itself shows, falling for ages toward a surface, except that here the falling has a destination and a purpose. When it finally arrives, Dragonfly will not simply drop and land. It will enter Titan's thick atmosphere behind a heat shield, slow under a parachute through the high haze, and then, at the right moment, let go and take up flight under its own power for the first time. From there it will begin its careful survey, testing the air and the ground at its first sight, then rising on its rotors to leap to the next, and the next, over a mission planned to last several years. Each hop carries it into terrain no one has ever seen from the surface, and each landing is a small act of exploration in the fullest sense, a machine setting down where nothing from Earth has ever stood. And through all of it, the question we have been circling tonight will be riding along. Somewhere on Titan, in the organic snow that Dragonfly will fly over and land upon, is the substance behind the fingerprint that matches nothing. The mission was not designed solely to solve that one puzzle, but it is exactly the kind of machine that could, carrying to Titan's surface the single tool that can weigh a molecule directly and finally tell us its name. The telescope found the question. Dragonfly may carry back the answer. Picture the day it arrives, because it is worth holding in the mind. The machine falls first under a parachute, dropping through the high haze, through the layered orange smog we have talked about all night, the same haze that has hidden Titan's face for the whole of human history. For a long descent it sinks through that veil, sampling the air as it goes. Then, lower down, it releases and its 8 rotors bite into the dense cold atmosphere, and for the first time a craft from Earth is flying under its own power beneath the clouds of Titan. The haze thins as it descends, and the surface resolves below it. Dune fields the colour of dark coffee stretching to a close, curved horizon, the ground softened under a blanket of organic snow that has been falling here since before our species existed. It settles, gently, onto a surface no eye has ever seen from ground level, in a silence broken only by the slowing of its own rotors, and somewhere beneath it, in that dark organic layer, is very likely the substance we have been chasing, the fingerprint that belongs to nothing, waiting to finally be read. There is even a hazard hidden in that image, and it is a real concern for the people planning the mission. The organic snow that coats Titan is soft, and in places it may be a metre thick, a fluffy, unsettled layer over the harder ice below. A flying machine that lands in the wrong spot could sink into it, or find itself in trouble on unstable ground. This is one of the reasons the discovery we have been discussing matters so directly. Scientists are using the very data from the Space Telescope, the maps of where this substance sits, to help understand the terrain Dragonfly will face, to learn where the organic material gathers thickly and where the footing might be safer. The snow that falls in the dark, the same snow we watch settling out of the haze, is now a thing to be navigated, a surface to be trusted or avoided. What began as a spectral curiosity has become a practical question of where, exactly, to set a machine down on another world. And so the mystery reaches forward in time. We may not have to wait for Dragonfly to solve it. The answer might come sooner, from a laboratory. But by the middle of the next decade, a spacecraft may be standing on the very material that has puzzled us, ready to tell us at last what it is made of. The fingerprint we cannot read from here may simply be read there on the ground by a machine we sent for exactly that purpose. Part 11. What it means that we can see this at all. Before we reach for the answer we do not yet have, it is worth stopping to marvel at the question, because the fact that we can even ask it is astonishing. Step back from the mystery for a moment and look at the whole situation from the outside. Sitting about 1.5 million kilometers from the Earth, far beyond the Moon, in a cold and stable spot in space, is a telescope. It is a single machine with a folded golden mirror, drifting out there in the dark, gathering light. And with that one instrument, without leaving its post, we pointed at a moon of Saturn more than 1 billion kilometers away, caught the faint sunlight bouncing off its hidden surface, spread that light into a spectrum, and found in it the fingerprint of a substance no chemist on Earth has ever measured. Then we turned to a dwarf planet nearly 6 billion kilometers away, a world that is barely more than a point of light even to our best eyes, and we did it again and found the same fingerprint waiting there too. Think about what that actually requires. The light we analysed left those worlds hours before it reached the telescope, crossing a gulf so wide that it takes light itself, the fastest thing there is, more than an hour to make the trip from Saturn and over 5 hours from Pluto. That light is unimaginably faint by the time it arrives, scattered thin across the enormous distance. And yet the instrument is sensitive enough and steady enough to measure not just that the light is there, but exactly how much of it is missing at each precise colour, precisely enough to detect a dip of a few percent at one specific wavelength, and to pin that wavelength down finely enough to know that it is the same on two different worlds. We are reading the chemistry of surfaces we will likely never touch, on worlds most of us will never fully picture, by the faint and ancient light they reflect. A few centuries ago, the very idea would have sounded like madness. It is worth understanding just what kind of machine makes this possible, because the telescope behind this discovery is one of the more improbable things our species has ever built. Its main mirror is more than 6 meters across, too large to fit inside any rocket, so it was built in 18 separate segments of gold-coated metal that folded up for launch and then opened out in space like a flower. It does not orbit close to the Earth, as many telescopes do, but sits at a special stable point about 1.5 million kilometers out, roughly 4 times farther than the Moon, where it can stare into the dark without the Earth and the Sun constantly interrupting its view. And it is built to see infrared light, the very range where our mystery lives, which requires it to be kept staggeringly cold, shielded from the sun's warmth by a sunshade about the size of a tennis court, so that its own heat does not blind it to the faint infrared glow of distant things. That is what it takes to catch a signal like this. The light reflected from Titan and Pluto is almost unimaginably faint by the time it crosses the solar system and arrives, and to pull a precise fingerprint out of it, you need an instrument that is enormous, perfectly cold, perfectly steady, and parked far from the noise of home. We built such a thing and sent it out into the dark, and now it reads the chemistry of worlds by their reflected light. When you hear that the telescope detected an unknown substance on 2 distant surfaces, this is the machinery behind that quiet sentence. A folded golden eye 1.5 million kilometers away, holding still enough to measure a dip of a few percent in light that left Saturn more than an hour before. There is a kind of reversal in all of this that is easy to miss. For almost the whole of human history, the worlds of the outer solar system were nothing but points of light, and we were the ones fixed in place, able only to look. Now we can sit at home and read the surfaces of worlds we will never visit, and even reach out and rule out, one by one, every substance in our catalogue until only the unknown remains. The looking has become a kind of touching. We run our instruments across a moon of Saturn the way you might run a hand across a texture in the dark, learning its shape without seeing it, and what we have felt this time is something we do not yet recognize. This is the quiet triumph hiding inside the mystery. We tend to focus on what we do not know, the unnamed substance, the unsolved puzzle, and that focus is natural and even useful, because not knowing is what drives us forward. But sitting right alongside the ignorance is an extraordinary competence. We built a machine that can detect an unknown organic material on the surface of a moon of Saturn from 1.5 million kilometers away. That we cannot yet say what the material is takes nothing away from the fact that we found it at all, that we can hold its fingerprint in our hands and study its shape and argue about its identity, all without going anywhere near it. And there is something almost dizzying in holding those two truths together at the same time. We can measure a molecule on a world more than 1 billion kilometers away, precisely enough to know it is real, precisely enough to know it is the same on 2 separate worlds, precisely enough to rule out every substance in our whole catalogue, and we still do not know what it is. Mastery and ignorance arrive in the very same breath. We are at once powerful enough to detect the thing and humble before the question of its nature. That is not a failure. That is what the frontier of knowledge actually feels like from the inside. It is the exact sensation of standing at the edge of the known, close enough to touch what lies beyond it, not yet able to name it. I think that feeling is worth sitting with, because it is rarer and more valuable than certainty. Most of the facts we carry around were handed to us already solved, and it is easy to forget that every one of them was once a mystery that felt exactly like this, a real signal without an explanation, a fingerprint without a name. Someone had to stand at that edge and be patient. The discovery on Titan and Pluto is a chance to stand there ourselves, in real time, to feel what it is like to know that something is true, and to be able to describe it precisely, and to still not understand it. The universe has handed us a well-posed question we cannot yet answer, and there are few things more genuinely exciting than that. Because a well-posed question is a promise. It says there is an answer, and that the answer is reachable. We are not staring into an unknowable void. We are looking at a specific substance, on specific worlds, absorbing a specific colour of light, made by a chemistry we understand in outline even where we cannot name its product. Everything about the way this mystery is shaped tells us it can be solved, and when it is, whether by a clever experiment on a laboratory bench or by a nuclear drone standing on Titan's snow, we will add one more page to the catalogue, one more fingerprint with a name beside it, one more piece of the story of how ordinary chemistry, out in the cold and the dark, builds the beginnings of complexity. The not knowing is temporary. The reach that let us find it at all is the permanent marvel. Part 12. The name we do not have yet. We have come a long way tonight, from a single dip in the light to 2 entire worlds, and we arrive at the end holding the same thing we started with, a substance without a name. That is worth saying plainly, because it is genuinely unusual. This material is so newly noticed, and so thoroughly unmatched, that it does not even have a name yet. We name things once we know what they are. We had no name for oxygen until we understood it, no name for the tholins on Titan until we recognized them. This substance sits in the strange position of being real, measured, mapped onto 2 worlds, discussed in a serious scientific study, and still nameless, because naming it would require knowing it, and we do not. Somewhere in the organic snow of Titan and Pluto is a thing that has been there for ages, doing exactly what it does, and it has been waiting all this time not just for us to find it, but for us to have a word for it. Think back to where we began, to that instinctive reaction people have when they first hear about a signal that matches nothing in science. This shouldn't exist. By now I hope that phrase sounds different than it did at the start, because the substance very clearly does exist. It is not a violation of anything. It is not impossible or forbidden. It is simply ahead of us, a piece of the universe that got here before our catalogue did. The feeling that it shouldn't exist was never really about the substance. It was about the comfortable belief that we had finished the map, that the chemistry of the solar system held no more genuine surprises, and that belief, gently, is what this discovery corrects. The substance does not need permission to exist. It only waits for us to catch up. The fingerprint that belongs to nothing, then, turns out to be a fingerprint that belongs to something we have not met yet. Those are very different statements. The first sounds like a dead end, a signal doomed to stay unexplained. The second is an invitation. It belongs to something. There is a real molecule, or a real mixture of molecules sitting out there with a definite identity, and one day we will hold it up against the right laboratory measurement, or read it directly with an instrument standing on Titan's surface, and the empty page in the archive will finally be filled in. The name exists already, in a sense. It is just written in handwriting we have not yet learned to read, and the snow keeps falling in the dark while we work it out. Right now, tonight, as you listen, the skies of Titan and Pluto are doing what they have done for billions of years, quietly assembling complex organic molecules out of nitrogen and methane, and letting them drift down onto the surface grain by grain, unwatched. The same slow snow on 2 worlds that have never touched, building the same soft dark layer, holding the same nameless substance. There is a kind of patience in that image that I find steadying. Whatever this material is, it was not made for us, and it does not wait on us. It is the ordinary work of 2 worlds going about their chemistry in the cold and the quiet, and it will go on whether or not we ever name it. We simply have the good fortune to have noticed. I find it worth sitting with the idea of a nameless thing, because we so rarely encounter one. Almost everything in your life has a name, was named before you arrived, sorted and labelled and filed by someone who came before you. To stand in front of something real and well measured and simply not have a word for it is a rare experience, and it quietly connects us to every earlier moment when people stood at the edge of the known and waited. There was a time when fire had no name, when the lights in the sky had no names, when the very air we breathe was a mystery without a word for it. Every name we now hold was once absent, and someone had to live in the gap before it arrived, the way we are living in the gap before this one. There is nothing frightening in that gap. It is simply the place where knowledge has not yet reached, and it is, if you allow it to be, a rather peaceful place to rest for a while, and it will not last, which is the quiet promise folded inside every well-posed mystery. The gap will close, the name will come. This particular strangeness will settle, in time, into the ordinary body of things we know, taking its place in the catalogue beside all the other substances that once seemed impossible and turned out merely to be new. But tonight, for a little while longer, it remains open, a small held breath at the far edge of the solar system, and we get the rare privilege of keeping it company before the answer arrives. The answer is coming, and it may come from either of two directions. In laboratories on Earth, researchers are already at work trying to recreate this signal, mixing organic materials under conditions like those on Titan and Pluto, tweaking the recipe, searching for the combination that produces a fingerprint at exactly 5.11 micrometers. It is quite possible that one of those experiments will find the match before any spacecraft arrives, and we will have our answer from a bench in a quiet room, a mixture finally assembled and measured. And if the laboratories do not get there first, then by the middle of the next decade a machine will be standing on Titan itself, ready to scoop up the snow and read it directly. Either way, the question we cannot answer tonight has a due date. This is not a mystery for the ages, it is a mystery for the next several years. So we end where we began, with a signal coming from two frozen worlds that nobody can yet name. But the meaning of that signal has changed across the course of our journey. It began as something unsettling, a thing that seemed like it shouldn't be there. It ends as something hopeful, a well-formed question with an answer on the way, a reminder that the solar system we thought we had finished mapping is still generous enough to hand us a genuine secret, and that we are patient and capable enough to eventually accept it. The dip in the light is still there. The name is still missing. But the missing name is not an absence anymore. It is a space held open, waiting to be filled, on a page we have already found. And there is no hurry. The snow will keep falling in the dark, on Titan and on Pluto, holding its secret gently, for as long as it takes us to learn how to read it.